Hello, let's continue from our previous lecture. In last lecture, we discussed primarily the how backtracking works. We took three examples. One was 8 queens problem, other was 3 color problem for a 5 node graph, and then we also look at sum of subset problems, that is given a set of elements and given a number, can you find those elements whose sum value equal to the given number. We look at how to build algorithm, how to look at the solution, how do we systematically using backtracking approach we proceed, and finally how does a generic algorithm for backtracking would look like. As usual, the resources are, we look at still section 7.1 from textbook 2, and there are other resources as you can look at the textbook 1 and book by algorithm. So let's look at what is that we really studied. What did we really do in backtracking? What we studied in backtracking is that there is a solution space, there are different solutions. We start from some position which looks a feasible solution, proceed and explore the solution space and keep searching till we find a solution. So how do we search the solution space? The method is you primarily build a tree of a solution space, start from a root node, go along different branches, and each node is kind of a state. Each edge indicates transition from one solution point to another solution point, and explore this tree, and when you reach a node where a solution exists, you probably found a solution. And then we look at basically how do we build this solution tree. So if you look at this tree, remember we started, when you look at our solution space for 8 queens problem, we defined that solution corresponds to 8 tuples. When we look at sum of subset problems, we define a tuple having 4 variables. So essentially, the tree looks at each edge corresponds to one tuple. We start from beginning start, there is tuple is empty. Then we look at first variable called x1, that will correspond to edge. So whatever possible values x1 can have, the root node would have that many child node branching out, and then we come to a state where x1 is assigned. Then we look at second tuple x2, we assign that value, take different values, and this is how we are saying we expand the tree looking at tuple variable. So essentially each edge of the tree corresponds to tuple variable xi, where xi is assigned a possible value, and when we reach a leaf node, the leaf node may satisfy a condition. If satisfies a condition, it represents a solution. Some criteria, like in 8 queens problem, we said no queens should attack each other, and if you find a tuple values, variable values, that none of the queens attack each other, we find a solution. Just because you find one solution, we can decide to stop there, or we can explore the tree further to find the other solutions that exist. As we'll go ahead, we'll find there are 2 kinds of trees. One is called static tree and other is called dynamic tree. Static trees are those which we build the trees and then explore. Dynamic trees are the trees, when you look at the problem, start building from the problem instance itself. So let's look at our 4 queens problem, a mini version of 8 queens problem, that is given a chessboard of 4x4. So this is our chessboard of 4x4. How do we place different queens here? How do we place in this chessboard of 4 queens? So one queen come in this column, one would be in this column, one is in this column, one is in this column. How do you place the 4 queens such a way that no queens attacks each other? And so we'll basically, what we want to do, for each column we define a tuple variable. For the column A, we define x1. For column B, we define tuple variable x2. For column 3, we define x3. And for column 4, we define tuple variable x4. So, and then we see what the values are. For x1, it can take value 1, 2, 3 or 4. Similarly, variable x2 can take 1, 2, 3 and 4, and that will assign the values. Let's take the case, this example, and how do we build with such a tree. So how do we start? We start from beginning position, start. Now we look at for the first column, that is tuple x1, and tuple x1 for the 4 queen problem, what are the possible values? It can be in row 1, or first queen can be row 2, row 3 or row 4. That means x1 can have value 1 or value 2 and value 3 or value 4. So first start with value 1. We build the edge, x1 is equal to 1. So we reach a node. Now we have to explore x2. Having x1 is equal to 1, x2 can again have 4 possible values, 1, 2, 3 and 4. But we start with a constraint that a no row can have 2 queens and no column can have 2 queens. That means since my queen 1 has gone to column 1 and row 1, x1 is equal to 1 means my queen is placed in row 1. That means my second column, I can have value either 2, 3 or 4. That means second queen can go to either row 2, row 3 or row 4. Once second queen takes row 2, that means my row 1 is occupied, my row 1 is occupied, my row 2 is occupied. So I look at third column corresponds to tuple x3, and what values can take? It can take either value 3 or 4. So let's assign value 3. We build an edge, and then reach next, and then if first row has been taken, second row has been taken, third row has been taken. So for the fourth queen, only possibility is row 4. So we assign this value. Now look, all these 4 may not be feasible solution, but we are just trying to build a solution space, explore what it is. Alternatively, we build this, or we can say that x4 has only one possibility, backtrack to 3. If for the column C, that's tuple 3, the tuple variable x3, I can take value 4 as the fourth row. So if I can take fourth row, which is here, then my x4 tuple variable can take value 3 and not 4. And this is how I build the tree. We exhausted both possibilities. Now we go backtrack to variable x2. x2 has taken value 2. Next possibility for variable x2 is 3. And then we build again. Now at this point, tuple variable x1 taken value 1. Variable x2 has taken value 3. That means my variable 3 can take either value 2 or a value 4. So let's build a tree with value 2, and then that means tuple variable x4 will take value 4, or alternatively the variable x3 can take value 4, and then variable x4 will take value 2. We can further backtrack, come back, we take another possibility, backtrack to variable x2, that is column 2. That means queen 2 can either go to row 2, or it go to row 3, or it can go to row 4. If it goes to row 4, x2 take values 4. When x2 variable can take value 4, x2 can take either 2, because value 1 is taken, first row 4 is taken, so value 4 is taken. That means only possible choices for x3 are either value 2 or value 3. If x3, that is for column C, value 2 is taken, then for column 4, that is variable x4 can take value 3, or if variable x3 takes value 3, then it will take value 2. We can go further. Now we have explored all 3 possible values for x2. Now you backtrack to variable x1. What is the next possible value for variable x1? Think about it. And if I build a branch, my next value should be x1 is equal to 2. When x1 is equal to 2, what are the possible values for variable x2? So if my value is for variable x1 is 2, the possible values for x2 would be 1, 3 and 4. That is, if my column 1, I put a queen on row 2, That means in column 2, I can put my values in either row 1, 3 or 4. So my variable x1 take value 2, then my variable x2 can take either 1, 3 or 4. And if variable x2 takes value 1, that means column 1 q is in row 1, column 2 in column 1 queen is at row 2, and column 2, which is variable x2, queen is in row 1. That means column 3, which is variable x3, can have value 3 and 4, and correspondingly. However, if when my column 1, that is x1, takes a value 2, and column 2, x2 takes a value 3, that means row 2 is occupied, row 3 is occupied. That means for column 3, I have possibilities for value 1 or 4, and that will build. Now continuing this way, pause the video, spend about few minutes, and you build the next part of this tree. So for x1 we already taken value 1, we have taken value 2. Now what would be the next value for? So we need to look at next value would be basically x1 is equal to 3, then build for values x3 and x4. Similarly, the values for x1 could be 4, and then you build those values. So please build a value for x1 is equal to 3, build the whole tree down the line, and then take the branch where x1 is equal to 4 and build the whole tree down the line. Spend 5 minutes, build those tree, and once you are ready, check back with your answers for this tree which you have built. So let's, assuming that when you build the tree, resume the video and continue how do you go about. So when you take variable x1 is equal to 3, tree will look like this, and when you take variable x1 is equal to 4, tree will look like this. And so look what we had done. Essentially what we had done, we have taken all possible values. So look at total possibilities are factorial 4. So we have 24 possible value, which is factorial 4. That means my size of state space for a 4 queen problem is factorial 4 is which is 24. If I have 5 queens problem, space would be factorial 5. For 8 queens, it is factorial 8. So let's look at what are the possible solutions. Now given this tree, this is a complete tree, we still do not know which one is the right solutions here. Whether my right solutions is along this path, or is along this path, or along this path, we don't know. We are simply build a tree yet. So we'll explore exploring this tree and see how does a solution can build up. So one feasible solution is you can look at q1 comes here, q2 comes in. So that means variable x1 takes value 2, variable x2 takes value 4, variable x3 will take value 1, and variable x4 will take value 3. So there are 4 possible values, and let's explore the tree which is built up to see how we can find the solution for the 4 queens problem. So we start with first value, which is x1 is equal to 1. That means queen get placed in the row 1, and x1 corresponds to column 1, x2 corresponds to column 2, x3 corresponds to column 3, and x4 corresponds to column 4. So we explore this tree. x1 is equal to 1, put the queen in first column, we explore, and that means we selected this branch and we taken this. Having placed queen in this, we look at the explore x2 is equal to 2 means can we place queen in column 2. One minute. So look at, can you place queen in column 2? We certainly cannot place in the column 2 because it is not going to work. So we stop this solution, don't explore further, because this queen, if I place second queen in value 2, this queen would attack and we can't build a solution. So let's look at next possible value. That means can I take x2 value 3? We explore the next branch And then yes, queen could be placed here. Because queen can be placed here, we explore further and then look at column 3, that's variable x3. Variable x3 would be 1 is taken by row 3 is taken, so I can look at row 2. Row 2 means I take x3 is equal to 2. Now if I put a queen here, this queen gets attacked by the queen in column 2. That means this queen cannot be placed. That means this branch cannot be taken, and we stop right there. The next possibility for x3 is value 4. And if you put in value 4 again, this position is attacked by the queen in column 2. So we can't even put it. That means both these positions are not there. So we explore next backtrack, go to value x2 is equal to, next possibility is 4. So we go to next possibility, look at, we move the queen to the column 4. And now we have x1 is equal to 1, x2 is equal to 4. What x3 can be? Next possibility is 2. So we explore this branch. When you explore this branch, can queen be placed? Yes. We place the queen in 2. And only possibility for variable x3 is value 3. But when you put this queen here gets attacked by this queen. So this is not feasible. So block it. Now next possibility, we backtrack. Look at what x3 can be. It was 2. Can you move to x3? Yes, we can move to x3. But if you move, this position get attacked by queen in column 2. So that means this cannot be taken. So we stop searching the next path. So that means we backtrack further. We have taken all possibilities 3. Now even for 2, we explore all the possibilities. So we backtrack further and now look, take next value of x1 to 2. That means I move this queen here to this position. So when I move to this position, consider this, and I move this queen to this position. So x2 is 2 now. I start with x1, start with x2. x2 can take value 1. But if I take value 1, this queen will attack it, so I cannot branch across this tree. Next possibility is, because I cannot place the same row, I take for x2 value 3. When I take for x2 value 3, this position again gets attacked. That means we can't proceed further, so we don't have to explore. Next possibility for x2 is value 4. So we take this value, we can place the queen there, which is fine. So we explore further. Now we have taken row 2 and row 4. This is for x1 is equal to 2. This is for x2 is equal to 4. So let's look at x3. Value we can take is 1. So we explore x3 is equal to 1, which can be taken. We assign the value, place the queen. Now all 3 are taken. That means for variable x4, that is column 4, only possibility is 3. Can we take this value? And yes, this value can be taken, and this gives me a proper success path. I got solutions for 4 kin problem. If you are interested only in one solution, we can stop here. But if we want to explore further, we can explore that way and continue. Now I suggest that having found a solution, x1 is 2, x2 is 4, x3 is 1, and x4 is 3. Can you explore other solutions? Spend 5 minutes, build their solution, search across these branches of the tree and see, identify which branch could give you the next solution. So continue this way and see which branch can give you next solutions and continue that way. So if we look at the space problem, and continue in that manner. So what we have done, if we look at what we really have done, we have basically built the entire space tree with all possibilities and then trying to explore. And that's what we essentially we had done. And the moment we come to a place where we could not explore because solution was infeasible, like we took x1 is value 1 and x2 is value 2, this position got attacked, so there is no point exploring value for x3 and x4. We stop there, say we stop the tree right there. And then we have backtrack to explore the next path and continue. And for the 4 queens problem, the moment we reach a leaf node, that means we basically found a solution. This may not be true for other problems. For this case, it works. So essentially, you look at, before we found a solution, we build the entire tree. And that means building my tree is independent of a particular sensitive problem, and this point will become more specific when you look at next set of problems. And let's look at the next problem is what is called sum of subset problem. So sorry, it is typo error there. It is called sum of subset problem. So let me correct this, just give me a minute. Now, in sum of subset, we are given 4 elements in the set 11, 13, 24, and 7, and we need to find those elements whose sum comes to be 31. Now, for each element, we have a choice whether we can select the element or don't take the element. So, for each of the element, we assign a tuple variable. So, we'll assign x1, x2, x3, and x4. Now x1 is equal to 1 means we take an 11, x1 0 means we don't take the value 11. Similarly, x2 is equal to 1 means we consider the value 13, we accept the value 13, x2 0 means we don't take the value 13. That way, can we build the entire tree? So we start from this position, build a tree, and look at x1 is equal to 1, x2 is equal to 1, x3 is equal to 1, x4 is equal to 1, or x4 is equal to 0, or x3 could be 0, x4 is 1. So look at, for each variable we have 2 possible values, 0 and 1. We have 4 variables, that means total possible solutions are 2 raised to power 4, which is 60. Now how do we explore this tree to find a solution? So we take variable 1, 2, 3 and 4. Let's look at the first case, x1 is equal to 1. That means we take the value 11, and yes, we still not 31, but we are less than 31. That means we have scope to reach 31. So explore next one. We say x2 is equal to 1, which is 13. So 11 plus 13 is 24. Less than 31. That means still have to search for another. Come to next one. Look at x3. If you consider x3, that means 11 plus 13 plus 24, it becomes 48. That means we already exceeded 31. We're not going to proceed further, so we can stop right here. We don't search it. This is what we do, and we don't search it, we block. That means we don't consider x3. We consider x3 0. That means we don't consider the 11, 24. The value is still at this point. Solution is 11 plus 13, 24. We don't consider this. So at this point, value is still 24. Let's consider x4 is equal to 1, that is 7. So 11 plus 13 plus 7, that makes it 31. So we found a branch tree following this path. We found a solution. Are there more paths we can explore? Does x4 is equal to 0 gives us this? No. Then we backtrack, look at x2 is equal to 0. So that means we have taken 11, we are not taking 13, but let's take 24. So when x1 is 1, x3 is 1, x2 0. At this point in time, my total sum is 11 plus 24, which is 35. If it is 35, that means we already crossed 31. So it doesn't matter whether x4 is taken or not taken, we already exceeded 31. So we don't have to search further, we block it right there. Let's say x3 is equal to 0. That means if we take x3, we can't reach. So we take x3 is equal to 0. So far solution is x1 is 11. Let's see whether x4 gives us a value. So we explore this, but it is, we know that 11 plus 7 is 18, which is not 31. We don't have a scope. So even though reach a leaf node is not a solution because it doesn't meet the requirement. Even if we don't consider element number 4, x4 is 0, my sum is still 11, we don't reach 31, we don't reach the solution. So we explore now, that means we take and explore all possibility x1 is equal to 1. Let's consider a solution where we don't take the element 11, that is x1 is equal to 0, and explore further, and continuing this way, we take x2 which is 13. Now we take x3 is equal to 24. So x3 is equal to 1, x2 is equal to 1, total become 37. We exceeded 31, so there is no point in exploring further, we stop there. That means I take x2 1, I don't take x3, so I consider this value. So my sum total is 13, x1 is 0, I don't consider 11, I'm considering 13. I'm not considering 24. Let me consider 7. 13 plus 7 is 20. Doesn't meet my requirement. If I don't consider element number 4, I still don't meet the requirement. So I take on both possibilities of not considering x1 but considering x2. It doesn't give me a solution. So go to next exploration where we also don't consider x2. And then my possibilities are I consider x3, which is 24, and I consider x4 is equal to 1, which means element 7. 24 plus 7, 31. This gives me a solution. As you can explore other branches, don't give us a solution. And that way, by exploring a tree, we could find a solution. So exploring this, first solution is tuple 1, 1, 0, 1, and second tuple is 0, 0, 1, 1. Sorry, again there's a typo there. Is not a dot. This value should be 1. Let me correct it. And that's where you found a solution. So let's essentially what we have done, if you look at, we basically in this problem, we first build a complete tree, which is a static tree, and this tree is independent of what my values of elements are. All we need to know is there are 4 elements in a set, and there is a one sum which I need to find, and we build because each tuple can take one value 0 or 1. So each variable xi can take 2 values. So if there are n variables, my total space size is 2 raised to power n. We explore one, look at the possibility. If we reach the solution which exceeds my total sum, I stop, don't explore, backtrack to go further. When I reach a leaf node, it's not necessarily the solution is found, as we found that sum total may still be fine. It's different from Twin's problem where leaf node indicates a solution, but in this case, leaf node is not a solution. Now please understand, building a static tree independent of the problem. So we took values at 11, 13, 24, and 7. If we do take even other values, let's say 12, 25, something of that kind, even then we don't get the solutions there. So that is where we basically find the solutions. So continuing this way, we'll basically proceed and see how we can really build a solution there. And essentially what I'm saying is, when you build a tree for all solutions, all possible solutions, that means when you build a tree for all possible solutions, that is called a static approach. So let's look at what building a tree. To make it live further, we need to use some terminology. Let's define the terminology. Now in our tree, each node in the tree defines a problem state which we need to explore. Some nodes will indicate a solution, but each tree, now solution would be from root to other nodes, that is called a state specific problem. Now solution states are when I go from root to a given node, that indicates my state. So these are possible solution states. Not every state is a solution, but these are indicate my solution. And any state, any path that indicates my criteria constraints, like some tuple values for some state problem, that some value becomes equal to desired value, that is my answer state. And the way I organize my tree is called my state space trees. So far we built static trees for both Twin's problem as well as sum of subset problem. Can we, rather than building a tree, static tree and exploring, we can build a dynamic tree. That means look at the problem, start building a tree. That means I don't have to do the entire work exploring. We basically build a tree, see feasible, and stop there when it's not needed. So dynamic trees are dependent on problem. Depending on the problem, tree structure will look differently, but for static trees are all fine. Let's resume back just a minute. So let's build a tree where we can look at the problem and then build the tree, and that is what is called dynamic tree. There are 2 approaches. First we look at backtracking, and in subsequent lectures we look at branch and bound as well. So essentially in the dynamic trees, we start at the root, generate other nodes, and explore the further nodes. So a node whose all other children are yet to be generated or being generated. To be generated is called live node, like root node, start node. Till I generate all, let's take the sum of subset problem. The root start node has only 2 branches. So as long as both branches are not generated, it is called a live node. Similarly, a live node whose children are being explored. Let's say I'm in the start node, I'm exploring x1 is equal to 1 or x1 is equal to 0. While this being explored is a live node. When I come to x1, any current node which I'm being explored is called a E node. And once I reach a place where I can't go further because it doesn't meet my requirement, or I reach a leaf which I can't even explore, that's called a dead node. So let's look at how do we build this tree. Let's consider our 4 queens problem to build this dynamic tree. We start, this video start from, put a queen in the first position. That means x1 takes value 1. Having taken this, let's assign x2 as value 2. When x2 takes value 2, we know this is not feasible because queen attacks this. So I don't have to build a tree. I block it right here, stop. That means I look at backtrack, go to next position, x2 is equal to 3. I build that branch, x2 is equal to 3. I can explore further. Now for x3, either a value 2 or value 4. Let's take a value 2. When I take a value 2, I know this value queen gets attacked by this queen, so we can't proceed further. We'll stop here. So backtrack, say x3 next value is 4. We build the branch s equal to 4. But again, this gets attacked. This is not feasible, so we cannot even proceed for x4. And that means you further backtrack, look at the value x2, which can be 4. So I explore, I move to 4, value 4. Now look at x3, x3 can be 2. Build the tree, x3 can be 2, and this is feasible. So look at x4, x4 can be 1, and which is not workable, or x4 can be 3. So look at neither 3, and 1 already done, so x4 can be only 3. So it's not workable, so we stop. But this leaf node, but not a feasible solution. Then look at next possible value for x3. It could be 3 there. I build there, and that means for value for x4 can only be 2. So this is 3, and value for x4 can be 2, which is not going to work out. And at this point, we have explored all these possibilities. So let's look at x1. Next value for x1 can be 2. So we backtrack, go to next value of x1 is equal to 2, and proceed. In this way, can you proceed, build the tree? That means x1 can be, I already taken x1 is equal to 2. So when x2 would be 1, so I build x2 is equal to 1, which gets attacked. I can't build it, so will not build the tree further, stop it. Next possibility for x2 could be 3. So I take the branch. Again, this gets attacked, so we can't build it further because it's not feasible. So we stop the tree right there. So next possibility for x2 is 4. We take the explore that next value, build it 4, and that means I can take x3 is equal to 1. I explore this, x3 is equal to 1. I build the tree, and then feasible. So take x4. X4 value can be 3 because row 1 is taken, row 2 is taken, row 4 is taken. So value for x4 would be 3, and in this case I build a tree, I reached a solution. I recommend you to explore further and see can you find other solutions. So pause this video, spend few minutes, build the tree, and see can you explore and build the solution. Assuming you have taken the minutes to build, now you can come with the solution, resume the video, and you can build your solutions to see things out. This is how the whole tree will get built up. x1 becomes 3, then x2 will become 1, then x3 becomes 2, which is not feasible because it gets attacked. That way you keep building it up, and you ultimately find a solution. And you find there's one more solution there, which is x3 is equal to x1 is equal to 3, and you explore the solutions. The x1 is equal to 3, and then x1 is equal to 4, so you'll have 3, 1, 4 and 2, you'll basically build, this would be the solution there, you can look at that. This way we have basic dynamic tree, and wherever we come to a dead end, we don't build a tree, we stop there. This is what dynamic tree, so we're not building the entire tree, we're building whatever is required. Let's build dynamic tree for sum of subset problem. Again, we have elements, as set has 4 elements and sum is 31. 4 tuples, each tuple can take value 1 and 0. We start with 1, x1 is equal to 1, that means value 11. I can take x2 is equal to 1, which is value 13. Now can I take x3 is equal to 1, this makes value 48. 11 plus 13 plus 24 is 48. That means we exceeded 31. We don't explore, we don't go further, we stop right there. So that means we take next value, x3 is equal to 0. Now so far value is 24 and we're not including third one. Let's take the third value, we build 7, this gives an answer, so it is a perfect answer. But x4 0 is not there. Proceeding this way, you take x2 is equal to 0. I suggest pause the video, take 5 minutes, build the complete dynamic tree, not complete tree, dynamic tree for this problem, and once you are done, you match the solution the way it comes out. Assuming you build the solution after 5 minutes, resume the video and match up what you build up and you find a solution there. So one solution is this branch, and other solution would be x1 is 0, where x2 would be 0, x3 is 1, so other solution would be this. We build it, but remember, we don't explore further, we stop. Now look here, even here all three we're still exploring. We know at this point, if values can't be meetable, no explore further, and there were the branch and boundaries. But considering this is how do we build a static tree using backtracking. Branch and bound will further prune this tree, we build a very small tree that's very effective. So you remember our 3 color problem, given the node, that each node can take possible 3 colors. The exercise is build a dynamic tree for this problem. I'm not given a solution, so take the exercise, build it and look at how the solution look like, and then what you will understand. So primarily if you look at what we're doing in backtracking, we basically start from root node, build it up. So we use a notation. So essentially x1 to xi is the path for up to first I variables, and let's say t x1 to xi indicates set of all possible values for first I tuple variables such that xi plus 1 is also a path. So if x1 to xi is a path to explore so far and xi plus 1 is a path, that means txi indicates a path in the set of all possible values. Clearly, if you look at this, t x1 to xn, because there is no xn plus 1, that's not a feasible solution, that would be fine. We further defined a boundary conditions corresponding to criteria, which a bi plus 1 is a boundary function predicate. If bi plus 1 is false, that means it's not a solution. We define that and proceed further, and you said t x1 to xn is false because there is no xn plus 1 node, don't explore. And essentially candidate for position xi plus 1, we look at it's a solution vector within this space. So till x1 to xi will find something, we'll stop there, we'll look at and build the solutions. So my algorithm is, I start from x1 is equal to 1, keep exploring till I explored all the variables, tuple variables, and then stop. So x1 is equal to 1, now look at is there a value of x1 such that it's a feasible solution, then yes, then increase k1, look for x2. If x1, x2 is solution, look for x3. If no, backtrack, go to x1, keep backtracking till you find k becomes 0, we stop. So this is basically a bulk algorithm, backtracking algorithm in generic. We look at more details in subsequent lectures. So in a summary, what we discussed, we basically say basic approach of backtracking is we build 2 kinds of trees, a static tree and dynamic tree. And static tree, we build the entire tree space and then look at the problem, search the tree to find a solution. Dynamic tree, you look at the problem instance and then build the tree. That's our approach. So suggest you that you understood it. To make sure you understand, build a tree for 3 color problem, then you understand completely.